So today's my topic is titled AI for Materials Discovery in Electronics. I guess in last uh, lunch and learn session, Ben gave a talk about the, the state of the art materials discovery approaches. This can be seen as a continuation of that, but I will focus more on what are the state-of-the-art AI-based models are and how they can be used in application in electronics. Let me introduce myself. My name is Atish. I'm part of April, where the vision of April is to develop and bring to market AI-based tools for boosting productivity across the entire electronics industry supply chain. So my today's presentation, I've prepared it in two parts. The first part would be just discussing through what are the recent and upcoming state-of-the-art AI-based approaches that are there out there for material discovery, and how we as electronics engineers can make use of them. And part two is more focused on what would be the prospects of these available AI models in more detail for electronics industry supply chain. In part one, I would be discussing many models and many databases. So there you will see many abbreviations and short forms. It's not important to remember them or what they are. The point is how we can make use of them. So you will see many of the short abbreviations and short forms. Just wanted to let that know. So the basic idea of AI-based materials discovery, and if you look at this, the way the AI-based approaches are being used, they follow this sort of a chain of thought. We want to find a material, we want to see whether it's whether it's suitable, and if it's suitable, we can check whether it's real, because AI-based material discovery is virtual. We want to see whether it also shows what we have generated through AI, whether it's real. So we need some sort of validation. So you can see for the first two parts, the finding a material and finding whether it's suitable, there is sort of a loop happening there. Find a material, see whether it's suitable. So based on the same chain of thought, we see the major AI-based models that are out there. So the first part is exploring materials, which is material generation. Most of the AI models are with that genre, in that genre. Second is assessing materials. That relates to finding out whether the properties of the materials are what we desired. And the third part is testing materials, and that's where the experimental validation comes into the picture. So in this part one, I will mostly focus on the first two parts. The third part I will just briefly touch on. Before going further, I think it's important to just acknowledge how important databases are, because our models are only as good as the databases that we use. So in general, for material discovery, we can find like these four sort of sources for materials databases, that being from scientific literature, X-ray diffraction data, computational data, which is DFT-based calculation, or experimental data. And this is an example of some of the databases that you see in each of this category. And this is not a mutually distinctive categorization that I've used, because some databases uses multiple sources. For example, Cambridge Structure Databases uses also scientific literature data, also X-ray diffraction. So this kind of gives us like a basic idea of just setting our expectations of when we are choosing an AI-based model. We want to make sure what sort of a database is being used for that model. I want to focus on material generation. I want to focus on material generation part, the first part of this this kind of a thought process, which are mostly AI-based model for material generations. Most of the material generator AI models generate materials in the form of a crystal. And the crystal is generally can be best mathematically presented as a graph, where the nodes would be atoms and the vertices would be the bond between the edges would be the bond between the atoms. So naturally, many of the algorithms are using graph neural networks, but these generative algorithms, we clearly see some of the most popular generative learning methods that are appearing in these models. So, for example, variational autoencoder is a very common choice for these kind of models. Another example is GANs. And recently, with Microsoft Research MatterGen model, we see this trend of using diffusion models. An important thing if you want to use this AI-based material generator, is to look at what they're actually doing. Here's an example of a variation autoencoder famous paper by King Ma, where it shows what latent variables are for, let's say, the digit recognition problem. So what we basically, the decoder part, which is the generator part, takes latent variable as the input, and it outputs the high dimensional image of the digit recognition. So the latent variable does two things. One, it represents the whole space of the high dimensional data. And second, it does that in a smaller dimension. For example, just a two-dimensional latent variable can represent this huge amount of images as you can see on the image. And the similar idea is used for material generators. We have some small dimensional latent variable, which is given as an input to the material generator. And as the output, we get the material structure that we want. Having said that, that most common choice for material generators is this graph-based kind of representation of material structure. There are some other models which use different form of representations. Some models use compositions and phase fields to generate the materials, while others may use voxelized images as well. Just wanted to mention that as well. So it's not all uniform. So our choice of model would also be based on what sort of a material representation that we're looking for. I wanted to move to the next part of assessing materials. So there are material AI-based models which can be used for property prediction. So once we generate a material, we want to see what sort of properties does it have, because we are more interested in the properties, the materials that will play a role in our applications. So I've made an attempt to classify these models based on what sort of material types they are more suitable for. And this material type is basically based on the choice of database that was used. For example, for MatterSim and MatterGen, both these models, the ICSD data was primarily used. So of course, the more suitable application for MatterSim would be when we are looking for inorganic materials. Another approach of figuring out what models that we want to go for, as far as property prediction is concerned, would be to take an image of what sort of material properties we are after for a certain application. Here's an example of some material properties that may be of interest for some, let's say, electronic device. And then we can use this information to sort of reverse engineer what sort of AI model is more suitable for this sort of a problems. For example, Genome, which is a Google DeepMind's material property predictor AI-based model, is useful for directly predicting these values, these material properties. Another example is MatterSim, which could be useful for some set of material properties. Here's another example of Align, which is used for another set of properties. Finally, PLFMF, which is more which was more specifically used for thermal properties. So you can see the thermal conductivity, thermal expansion coefficient for PLMF. So different models cater to different property predictions. And that also plays a significant role when we're trying to choose what sort of AI-based model we want to use for property prediction. I also wanted to focus on the mapping aspect. Previously I mentioned that not all models are using just crystal structure or CIF files as an output of material generation, or maybe as an input to property prediction. So there is a variability there. So I just wanted to mention a couple of methods that can be used for mapping, which I think will be useful in this pipeline. When we want to go from generation to property prediction, we may have to use mapping. Now, mapping from CIF file to voxelized images and compositions is pretty straightforward, because CIF file has most of the information that could be needed for compositions, and voxelized image can be formed just by giving highest probability density at the atomic locations, which are the coordinates which are given in CIF files. The other way around is a bit tricky, but for example, mapping voxelized images to crystal structure or a CIF file, there are certain libraries like Vestra, Crystal Maker, which are open source and they're easily available. Composition to crystal structure mapping is a bit tricky, because there are many assumptions and constraints that takes place. For example, we may want to constrain on what sort of a space group we want to constrain on. MatterGen have a fine-tuning, does give a fine-tuning feature for this crystal structure prediction pipeline. So we can use our own data to use MatterGen so that we can use it for crystal structure prediction. And of course, there are other machine learning-based approaches like CrySpy and CrySpay, which are out there. Another aspect that we may want to consider while we are choosing an AI-based approach for material discovery is the kind of data we have. Most of the data that we have is computational data, which is DFT-based calculations. The image that you see here is a representation of example of ICSD catalog. I found this sentence in the genome paper by Google DeepMind, where they mentioned the proportion of computational data and experimental data that we have available. We can see almost even less than 10% of data is actually experimental. And as engineers, we should be more focused on getting more data, like a computational data. Based model. So if the corrected model property that we're looking for, which is shown here in black color, most of the AI-based approaches that do property prediction would need to be corrected based on how far they are from the experimental data. We can make use of the small amount of experimental data that we have to do this prediction of delta, this delta term in this equation. So far, I haven't done so much literature survey on this topic, but I'm pretty sure there may be some approaches which are already out there. If not, this is a good low-hanging fruit for people who want to do research in material discovery. Lastly, we may not need this loop of generating material and predicting property one after another, because many of the AI-based models also have something called as conditional encoding, where not only latent variable is used as an input to the material generator, but some desired properties. So based on this condition desired properties, we will get the materials that we want. So this may narrow down our search for materials and may be very helpful for us. The challenge of that approach is that many of the models have chosen some specific properties that they want to condition on. So if you want to have a spectrum of material properties that you're interested in, you may not get all those all those properties conditioned in your model, because all some models even specialize in some sort of properties like thermal properties or magnetic properties, etc. So that could be an issue, but this is an interesting approach, and that would be definitely helpful to us. As far as the last part of testing materials, I haven't done much of the much effort into that part, but I just wanted to just bring your focus to this a mobile robotic chemist. This is a robotic AI-based robot that does the testing of the material. This is a video of Andy Cooper, who is the head of Cooper Lab in University of Liverpool. So I'll just play a small. I'm not sure if you can hear the. Can you hear the voice of the video? No, then maybe I'll just talk it over.
Yes, I can.
Yeah. Well, basically, he's trying to show how this AI-based robotic approach heavily increases the throughput. So in that video, Andy Cooper was showing how this this approach could test around 160 samples, I guess, in just 48 hours, which I guess, and if you want to do it manually, it takes hardly 2 samples a day, based on the mood of the person who's working on it. So that's an interesting approach there, that interesting research direction that we see in use of AI in testing materials. So just to summarize this AI-based material discovery models that we have so far, I've discussed this basic thought pipeline that appears in materials-based AI-based materials discovery approaches. We discuss how we can use it for material generation, property prediction. We may also need mapping of material descriptors based on the kind of a model we choose. And also, I also touched on how there is a need of a sim to real correction of the property prediction, because these property predictions are mostly based on DFT sort of simulations. So they are virtual properties, and in reality, we may want to correct them. So this is the end of the part 1 for my talk. But if I put the hat of electronics engineer, the natural question is, how would it be useful for electronic engineer? Because the AI-based model that were presented so far answers this question of how can we generate materials for some desired properties. And as an electronic engineer, our focus is not generating materials, not necessarily generating materials for some desired properties, but rather generating materials that are applicable to our application. For example, device design or in circuits and electronic systems. So the part 2 is more focused on that, how these AI-based models, where do they fit into the picture for an electronic engineer? So I just wanted to give like a broad perspective of how would electronic supply chain would look like. The way I visualize this is the planning of an electronic system would be from a top-down approach. So the planning would start with the system, circuits, and that boil down to the device. Once the overall plan is ready, the detailed design, I think, can go from bottom to top. But again, this is not as simplistic, but I'm just presenting one way of looking at it. So and for that reason, I wanted to use some sort of a example while I'm talking through how we can use AI-based material discovery for electronics. So I'm choosing to focus on how materials discovery would look like during the device design phase. But the concepts that I would be talking in the next few slides also applies to these upper levels of this hierarchy of detailed design. So you may just have to replace the device with circuit, but the idea would be the same. So for material discovery for devices, there are two main things that we want to look for. We want to choose materials that are more suitable for the device design at hand. And secondly, we want to choose a material that's more suitable for the fabrication as well. We want it to be easy to be fabricated. So the first part, which is choosing material for device design, since we want to choose a material for device design, we also the problem of material discovery goes hands in hand with the device design problem. The optimization problem for this in this case would look something like this. Like we would choose some material, choose some design parameters for a certain device, run the simulation, and then compute the figure of merit. And the optimization problem would be to maximize the figure of merit for the parameters of material and design parameter X. And the optimization method would be iterative. Most of that optimization method, whether it's gradient-based or gradient-free, are iterative. So they are shown with a loop here, and I represents the iteration of a optimization model. So in each iteration, we would start with generating some material, some device parameters, put that into the simulator. I'm here, since we are talking about how we can use AI-based approaches, I'm replacing the simulation with an AI-based model. This is just a speculative kind of a way of how we will actually use AI-based methods for this sort of a problem. One thing that I've done here is I've colored the elements where we would use AI-based approaches. So the pink part and yellow part of material generation and property prediction I've already discussed in part 1. So we can make use of the state-of-the-art AI models here, which are more applicable to our devices. The blue part is the thing that I think we need more work on as electronic engineer. Is we need these devices because this iterative process is quite expensive. The simulations are quite expensive computationally. So we would need some sort of new approaches for this. So if we want to answer this question of how we can leverage the state-of-the-art AI-based model, the answer would be choose this pink and yellow models from the state-of-the-art material discovery. But we still have this open question of how do we deal with the blue part. The solution of this optimization method is, of course, the optimal parameters X and the optimal materials for the device design. Another confusion that I see coming in material discovery when it comes to the fabrication. The fabrication process, unlike the device design process, is not just an optimization problem. It's more of an optimal control problem because fabrication is a dynamic process. So if you take an example that I've used as an illustration here, the fabrication would look something like this, where F is a state of the fabrication. Let's say, take an example of fabricating, making a choices of deposition and etching. So we may have a fabrication simulation that runs from time step 0 to time steps capital T. And at each time step, we want to look at the state of the process. And based on the state of the process, we want to take an action, which is shown with parameter P, so the process control. So for example, in this case, the process control parameter would be the choice of whether to go for deposition or etching. So this, and at each control step, we will look at the previous. So for P0, we will look at what is the state F0, or PT, we will look at the state of FT. So when we are trying to solve this optimal control problem, we are not trying to find the optimal values of M and this array of P0 to PT minus 1. Rather, we are trying to find out the value of M, what is the optimal material M, and the mapping between the state F and the process control that we want to see, because this is a dynamical process. The choice of P based on where we are in the system. So that's something that we have to discern when we are going for material discovery for device fabrication, as opposed to this optimization problem that we discussed before, which was materials discovery for device design. So because the problem itself has manifests itself differently in fabrication process, of course, the approach that we would take to solve this approach would be different. So here, what we're trying to optimize, is a policy pi that maps the state of the process, the fabrication process F, to the process control. So when we are doing the fabrication, we want to look at what is the current state of fabrication, and based on that, we take the control. For example, if we think we don't need a position, we can stop it and start maybe etching process, and vice versa. So the process would look, it's also an iterative process of finding out the best policy pi for the mapping, and also finding out the best material. The materials is generally selected at the start of the time step, the 0th time step, and then we run it through the simulation to check for how this policy that we have in the iteration I would look like. We transition the states of the fabrication process from time step T to the next one. And then we keep doing this process. And the aim is to find out the optimal material and optimal policy for process control parameters. This is an optimal control problem. I guess the most suitable solution for this one is reinforcement learning, where in reinforcement learning, it's basically solving the same optimal control problem from the optimal control theory, but more generalized, where the function approximators for value functions are used. For example, the policy pi in deep reinforcement learning would be represented by a neural network. And in reinforcement learning, we also have approaches like model-based reinforcement learning, where we learn the model of the process transition. So this is also an AI-based approach. So I use the same theme that I used in this slide here, where I used colors to show what elements, in which elements of the problem we want to go for AI-based approaches. I'm using the same approach here. Again, as we've seen before, the material generation, the pink element and the yellow element, we have already good enough research out there. And we have many property predictors and many material generators. But the blue and green parts are problem specific. They are more related to the fabrication of the device that we're considering. And this is something that we have to identify as our as what we should focus on when we want to go for materials discovery. So at the end, of course, the solution that we're looking for of this approach is the optimal material and the optimal policy for process control. I wanted to summarize just these two approaches. I presented them separately, but they go hand in hand, because the material discovery is being done for the same device, for example, in this case. So we may have to consider how is there a possibility of combining these two approaches. So far, the speculation that I've provided is based on what are the AI-based elements that we need to focus on. And I've just listed them here, and I've highlighted the one where I think there is more scope for electronics engineer to focus on, because most the material generator and property predictors AI models, there seems to be, we can leverage whatever state-of-the-art AI-based models we have, but we may need to focus on these last two parts. I also wanted to just point out the AI model. It may seem like this, the green element here and the blue element here are basically just like a AI-based model for simulations, but there is a distinction there. They are basically just sort of replacing the first principle based simulations, which are compute intensive, yes. But the difference between the two approaches is one is the full simulation and the second is the transition from one time state, one control step to the next one. And also when we are generating the policy, we don't need data for this, the last line in AI-based elements for US fabrication. So the AI-based approach that we would use for policy, the data generally will be just used from the simulations data. We don't really need a separate database. While for the digital twin, we may need data. So that's also something that we need to keep in mind. Yes, another thing, and I think this is important, is that since this space is so new and the challenge is of compute power, because using AI-based approaches means also providing a solution for compute-intensive processes, in these optimization problem and optimal control problem. And I think as the researchers who are just starting to explore this AI-based space for material discovery, we may want to have some solid benchmarks. And these benchmarks may vary from the completely computationally light problems to compute intensive. Because if we start our research directly in the processes which are heavily compute intensive, we may lose our effort. So we may want to start with simpler benchmarks, and then apply the same ideas on top of it. I had this experience during my PhD, my PhD was focused on using reinforcement learning for simulation-based control problems. It's very similar to this. And one of the main challenges that I had was because as engineers, we want to solve real problems. And my first year and a half, I just focused on a bigger problem, and I realized I have to slow down. First, create simple toy problems, work on them, and then apply my idea for a bigger problem. So maybe the researchers who would be interested in this, we can learn from my struggle that I had during my PhD. So just wanted to summarize my presentation. This is the end of my presentation. I wanted to give more time for discussions if you have any questions. This presentation is more of speculation from my side. So I would like to have your feedback. So the part, I'll just regroup what I've said so far. The part one was more about going through this thought process of the state-of-the-art AI models that are there for material discovery. Their focus is mostly on building models that can generate materials, even randomly in some cases, and then property prediction using the databases that we have so far. So these elements are there, we have, but they are not task specific. I think even the benchmarks that we have for these AI-based models acknowledge this fact. For example, the mat bench discovery, they are in the limitations of their mat bench discovery. The mat bench discovery is a benchmark that has been set for property predictions, and many AI-based models that are upcoming, they submit their models for a competition for this problem, but they're all for property prediction. And I think the need for the benchmarks which are more suited for task-specific problems, I think that's missing even now. So that was the part one. The part two, and identifying that need, I think part two would be this discussion that we should have of how we can leverage the current models and use it for electronic supply chain specifically. That's that also fits with the research work that I'm doing with April. I focused on the device design and fabrication and identified the difference of approaches that we may need when we want to use AI-based approaches. That was specifically just in the context of devices, but the same idea applies to circuit level or system level material discovery. These are the references I've used. Most of them are just the AI-based models and databases that we have that I've used in this presentation. And with this, I will leave you here if you have any feedback, any questions, or anything that you would like to add. For those who may not be interested, who may not want to show because it's getting recorded, I've also given my email, so feel free to get in touch with me later if you would like to, if you would like to discuss something more.